5.2 talks about a subspace that's a perpendicular space. So I think I just want to give you a few examples, but not really talk about it too much, and try to include a graph in this example. So here they define a subspace, and they don't say it's a subspace yet, but eventually they'll say it's a subspace. So let's start off with just a regular subspace. W is a subspace of Rn. We say that a vector V in Rn is orthogonal to W if V is orthogonal to every single vector in W. The set of all vectors that are orthogonal to W is called the orthogonal complement, denoted by W with a perpendicular sign, and people usually call this W perp. So in those cop shows, when they say we're looking for the perp, they're looking for something that's perpendicular to something else. So, I guess I don't need the graph. We can just draw things out. We can go in R2 or R3. Let's go to R3 and attempt to draw things here in 3 dimensions. And what are the possible subspaces in R3? There should be 1, 2. So it's either the point, which is like a degenerate subspace because there's not very exciting, a line going through the origin, a plane going through the origin, or the whole space itself. Okay. So let's go through all those. Well, let's go through the proper subspaces first. The proper non-degenerate subspace. Suppose we have a line as a subspace. W equals a line, whatever the line is. Then so W would be all these vectors from the origin to somewhere on this line. So basically it's just a scalar multiple of a vector that defines that line. What do you think W perp is going to look like? What? What is W perp going to look like? Yeah. No. A what? Plane. It'll be a plane. Some more about the plane? Perpendicular to that line, right? And one more piece of information about the plane? Passing through the origin. Okay? So W perp would be plane perpendicular to the line passing through the origin. Okay? And so if you have a plane to start with as your subspace, then your W perp would be a line perpendicular to that plane passing through the origin. So I guess we don't need to talk too much more about this. That's the general idea behind this subspace. And it's an interesting subspace to discuss if we were diving more into subspaces, but subspaces doesn't come up until after 5.4 for some reason. And so we're just going to talk about perpendiculars. Yeah?
Is this plane like the surface area of the cylinder around?
No, it's just the plane. There are no cylinders.
Totally like
Yeah.
that.
Yeah. So your W perp would just be this plane, provided that this is perpendicular.
Okay.
Just draw that little square over there, and it becomes perpendicular, right?
This is a line. Can't it be perpendicular in that direction? Like perpendicular in that
Well, the thing is that if you have a line, you want W perp is going to be all possible vectors that's perpendicular to this line. So it could be this line, or it could be that line, or it could be this line, as long as it's perpendicular. But now if you take the collection of all those possible vectors, they actually become that plane. So imagine this vector being spun around, and then now you got the whole plane. Or whatever. Do you see a cylinder?
It goes around, you know.
Oh.
But, wait, I get it. It's kind of emanating out like this. It's not.
Yeah. It doesn't stop. So you might see this circle thing, and then, well, first of all, it can't be a cylinder because we're stuck at the origin. Second of all, you can have any size, so it's not just restricted to that one disk.
Because it has to go to the origin, it's going to be in the second picture.
Yes.
That took a while. Okay.
I guess I should have drawn the graph on the.
Yeah.
It's too late. I've already spent enough time on this. Okay, so that's the idea of that perpendicular subspace. Now, it didn't say that it's a subspace, but in a couple of theorems from now, they say it's a subspace, so that you can prove that it's a subspace. But we're not going to do any of that. We did. What was the last thing we talked about last time? That would be Monday, right? You guys remember what we talked about on Monday? So long ago. Linear algebra. Orthogonality, and stuff like that. So, in all those theorems that were presented, you always assume that you have a list of vectors, and the list of vectors are orthogonal, or the list of vectors is orthonormal. Okay. What if you have a list of vectors that are just vectors? I mean, linearly independent vectors, but not necessarily orthogonal vectors. So let's try to approach this with an example and see if I have any drawing skills. So let's let B. Yeah, a set of basis vectors can be any vector, and they don't have to be orthogonal, as long as they're linearly independent. So let's say 1, 1, 0, let's go to 3D, and 2, 0, 1. So let's dot them. Okay, I dotted it in my head. It's not 0, so it's not orthogonal, right? So let's call this V1 and V2. So V1 is not perpendicular to V2, but they're linearly independent. So this thing, the span of this is going to be forms a subspace of R3. Okay. Is a subspace. Okay. So what does this subspace look like? A plane. You have two vectors in R3. The span of this is a two-dimensional plane. So the plane contains these two vectors. Good so far? Now, I'm interested, let's see if I can draw this, 1, 1, 0, and 2, 0, 1. So this thing forms a plane. That's the subspace. And they are not perpendicular to each other. how do you say not perpendicular in the drawing? Well, let's just say they're not perpendicular. So the idea is, what if I want to span the same plane, but I want these two vectors to be perpendicular? How am I going to make these two vectors perpendicular to each other? What? We're going to, not quite. It's going to be a process that we're going to talk about. So let's see if I can transfer this picture. What if we look at this plane from above, or perpendicularly, so that we're looking at the plane flat? And I'm imagining that these vectors might look like this. And they're not necessarily perpendicular. But now I want to create a basis vector that is going to be perpendicular. I want to create a basis, a set of vectors that is going to be perpendicular. Okay? Are you guys with me with this idea? So I want to create two new vectors. Maybe just for ease, I'll make the first vector to be one of those, v1. But now I want to create another vector that's going to be perpendicular, v2. Oh, wait. I'm sorry. I'm getting my u's and v's here. I call these v1 and v2, so I need to call my original non-perpendicular vectors v1 and v2. And then now I'm calling the new vectors that are supposed to be perpendicular u1 and u2. So want vectors perpendicular and span the same plane. Okay? So the first step, oh, by the way, just to look ahead, we're going to span the same plane, and these vectors are going to be perpendicular. And if we want, we can just shrink them down to unit length, and then everything would be okay. So then I have actual orthonormal basis for the same plane that I'm looking at. All right, so what would our first step be? I want to find u1 and u2. What's the easy first step? I have v1 and v2. What can I say about u1? It's just equal to v1. So let's start with that. That's always a good place to start when you're just letting one of your new things to be the same as whatever the old thing was. So now here's where the tricky part comes in. I have u1. Let's take a look at what I have right now. I have u1, which was v1, right? And then I want u2 to be a vector that's perpendicular to u1. So we have some tools like the projection tool, right? We can project, I don't know what this is yet, but if we project this down here, look at this projection vector, not a projection vector, but look at this projection over here. This looks like it makes a perpendicular line, right? And so maybe we can figure that out. So the projection, let's do this in a different color because this isn't our answer yet. This is the work that we're going to do to get to our answer. Green. The projection of v2 onto u1 will give us this vector down here. let me put U1 a little bit longer here, just so we don't. We can generalize this because they're not, U1 isn't necessarily going to be the same length as V, whatever. So the projection of V2 onto U1 looks like this. This is the projection, right? Now, if I want to make a vector out of this, do you guys remember the formula for the projection? It's something like the dot product of those two, right? V2 dot U1 divided by, so the magnitude squared. Yeah, so you got to multiply this by a vector. This is,
There's 2 lines around.
so it's in the direction of U1, right? So that's this green vector right here. And we have the green vector here. We have the V2 vector, which is right there. Hey, with those two vectors, can we create this new vector that's actually perpendicular to U1? It's the subtraction, right? This is head minus head. So what are we subtracting? Let's see. I want this vector that is essentially going to be this U2 vector, right? If you do the subtraction carefully and correctly in the right order. So U2, I'm not putting arrows on my vector, sorry. Figure it out. So what minus what? V2, it's head. I want my vector to look like this. It's going to be head minus the tail. But instead of U1, because U1 might be over here, I want that projection vector. Yes?
What would that green vector look like had you not multiplied it by U1?
It wouldn't be a vector because the dot product over a dot product is a scalar. And so it wouldn't, we would just find the length or something about the length of that.
Okay, so the stuff inside the parentheses is telling the vector to be this length regardless of the direction,
Yeah.
and the U1 is...
The U1 gives the direction. So what you're doing is you're essentially scaling U1 so that the shadow of V2 onto U1 is going to be of that length. Okay? So that's it. So now if we change our picture to these two vectors U1 and U2 and completely ignore the V1 and V2, then these two vectors are perpendicular and they would span the same plane. Right? Okay. So that's good. This is the formula that we want, or something like this. So what we have done here with only two vectors is we've successfully changed your basis. Now instead of the span of the basis vectors B, this is now we have the span of U1 and U2, which are perpendicular. Okay? All right, good. I gave those actual vectors as an example, and I forgot to work them out. You know, 1, 1, 0, and 2, 0, 1. Should we do it? Let's do it. I hope it's easy. So U1 is essentially going to be V1, which is 1, 1, 0. And then U2 is going to be V2 minus V2 minus U1 divided by U1 dot, or not minus, sorry, dot U1. So V2 is 201 minus, let's take the dot product of V and U. One of this is a V2. Sorry, this is a V2. I was looking down here, trying to match it up. So V2 is 201 dotted with U1. So it's basically V1, V2. So that's 2 divided by, and then U1 dotted with itself, 2. And then U1 is a vector, 1, 1, 0. So basically just subtract 2 minus 1 is 1. 0 minus 1 is negative 1. 1 minus 0 is 1. So this is U2. And between this first one and the second one, the U1 and U2, they would span the same space, which is a plane. They would span the same plane as these two vectors that we had originally started off with.
What's the example? I was going to say it's a good exam problem.
Are we going to ever do like more than 2 if we are going to have like 3 on the dimension?
Okay, yes, yes, yes.
I just wondered, like, are we doing 2, 3? I don't know.
So actually, the exam problem is going to be our next discussion, which is now to put this in the matrix. Oh. But it's the same process. But we're not quite finished with this idea yet. Okay. So what we did was we, quote, orthogonalized a set of vectors.
Why did the whole movement like are we going to do it in like
Yeah.
we are on the
I don't know. Okay, so the idea here is that this is an orthogonalization process which takes a set of basis vectors, and it's not, we're doing this in 2 and 3D, we're doing 2 vectors in 3D just for the sake of visualization, but technically this could be any size vector in any size space as long as the space is bigger than the vectors. But we can have 4 vectors in R5, for example. And it's going to be an orthogonalization process. Now, we only did 2 vectors, which is easy to visualize, but then there's another step where if you had 3 vectors, you can orthogonalize 2 of them and then orthogonalize a third one going through the same sort of process. Twice or 3 times, depending on how many you have. But if I have 3 vectors that I want to orthogonalize, you're going to do this 3 times. Say it again? In relation to the first one. So you pick one of the vectors, preferably if if there's no order in particular, you pick the nice vector if there's more zeros in one of the vectors. You pick that vector to be your base vector, and then you start orthogonalizing the other vectors around that. Okay, so that idea is discussed at the end of 5.2. So if you want to look at your book, I don't know exactly what page it is, but this idea of orthogonal component business that I'm not going to talk about. But I do want to jump to 5.3, and this whole idea expands to more, and it's called the Gramschmidt process for orthogonalization. So what we did is just the first two. And then if you have more vectors, then you would go through the same process. Okay.
I figured out what the defective answer is. Well, it's the wrong answer. It's the one in the back of the book.
Okay. So this is the process. Now, like I said, we did just the first two steps here, but if we had more vectors, actually, since we were dealing with three-dimensional vectors, we can only have as much as 3 vectors, or 3 of these steps. But if you had higher dimensional vectors, you can get more messy with this stuff. So it sounds like we need to do that homework problem, so let's take a look at that homework. Have it ready? No.
You can log in on my account if you want.
Okay.
Number 3 is wrong, the answer. It is defective. The answer that they accept is different than the actual answer.
Okay, well, what we're doing applies to number 2. And then,
Wait, but I thought you said this was the Gramschmidt process.
yeah.
Okay.
So number 2 is Gramschmidt.
But so is number 3.
But so is number 3. But number 3 is in the context of a matrix. Okay, let's do number 3. Yeah, so this has a defective sign on it, apparently. Yeah, so we'll do this as an example. Oh, exam problem? Getting closer. The exam problem is going to be a QR factorization, which involves this process. No. All right. Use the Gramschmidt process to find orthogonal basis vectors for the column space of the matrix. So what we want to do is we basically want to treat the columns as this as the vectors that we're trying to orthogonalize. And just by inspection, if you dot the first 2, they're not orthogonal. So you probably will go through this process. So we'll call this, I don't know what they call it, X. X column matrix. Okay, so x1 equals 0, 1, 1. So let's call our new orthogonal set of vectors Q1, Q2, and Q3. So let's call this Q1, and remember that the first vector is exactly the first vector of the original basis. So these are my basis vectors, and so my first vector for my new orthogonal set will be just x1, which is 0, 1, 1. Q2, now here's where we start doing the Gram-Schmidt process. Q2 is going to be x2, that vector, that new vector, and then here's the projection, x2 minus the projected vector. So it'll be x2 dotted with q1 over q1 dotted with q1, and that's going to be scalar times q1. What is that? x2 is 101 minus x2 and q dotted together, that's 0, 0, 1, and q2 dotted with, or q1 dotted with itself is 2. So there's a 1/2 there. And q1 is 0, 1, 1. So this turns out to be 1 minus 0, 0 minus 1/2, and 1 minus 1/2. So that's Q2. Oh, maybe I didn't want to call it Q yet. Oh well, we'll call it Q. So this is Q2. All right, Q3. This is the stuff that we didn't really explain with our process, but if we just follow the formula, Q3 is going to be, it's kind of like a combined projection of the third vector onto the other two vectors that's going to make it perpendicular. So Q3 is going to be, wait, what's the formula? That stuff. So it's going to be x3 dotted with q1 over q1 dotted with q1 times q1 minus x3 dotted with q2 over q2 dotted with q2 times q2. Now, before I dive into this, I'm looking at Q2, and Q2 is 1, negative 1/2, positive 1/2, which has fractions. Okay? Now, I think without losing any perpendicularity, we can scale this vector. Right. So let's take a modified Q2. They call it prime, I think, in the book, where it's Q2, the original Q2 times 2, just so we don't have any vectors and our calculations would be a little bit easier. In this case, you know, I think we can handle this calculation, but when your vectors get longer and you start having square roots of 17 or some weird number like that, then it might be good to do these scaling things. So without losing any information, we can just deal with an easier Q2 in our calculations. So x3 is negative 1, negative 1, 0. And then x3, that's x3 dotted with q1. That's 0, minus 1, 0. And then q1 dotted with q1, we did that already. I think we got a 2 for that one. Yeah, because if you do the scaling in the projection, right, it doesn't matter. It'll change the length of that, but then the change of length will also be taken care of in this projection. So it'll still project perpendicularly. Yeah. Yeah. So instead of, you know, this is where you're projecting it on, so it doesn't really matter where your vector is. You're still going to project it on to there, and it's still going to be perpendicular. Okay? Yeah. As long as you do everything here with the Q prime. So, or the Q1, 0, 1, 1. I had to change my, I was drawing parentheses for my vectors and then figured I should draw these brackets. All right, now this is the new one, x3 dotted with Q2, or modified Q2. And so that gives -2, +1. So that's a -1. And then Q2 dotted with itself. This is a 2, 4, 5, 6. And then Q2 is 2, -1, 1. So had we kept this other one, we would have gotten a different value for your scalar, which would give us the same vector here. All right. So this is going to be -1, -1, 0, minus, minus, so let's call that a positive, plus 0, 1/2, 1/2. Another plus, plus, or negative, negative is a plus. And then we get 1/3, -1/6, positive 1/6. Boy, just confused myself with those negative signs. So I hope this is right. I got a -1 plus 1/3, that's -2/3. And I have 1, 7, 6. -4 over 4, 6. -2/3, and then, yeah. These are both positive, so. What? This one or the last one? Okay. So if we're doing this one more, then we might consider scaling this to make it an easier vector to work with. But we're done, so we can just leave it like this. So I think the answer could be a lot of different things. The first one being 0, 1, 1. The second one being either one of these Q's, Q2s, Q2 or Q2 prime. And then the third one would be this, or some scalar multiple of this. Since we are just talking about a set of basis vectors, there's no restriction on the size, right? But if for some reason you want it normalized, then you would have to go to each of those vectors and normalize it. How would we normalize it? Let's actually normalize it. So this is the normalized version is what I wanted to call Q. I kind of jumped the gun and called it Q from the beginning, but let's call this Q1 normalized is basically taking this vector and then dividing it by its magnitude. So root 2. Zero, 1 over root 2, 1 over root 2. So that's the normalized Q1. I shouldn't call it Q1. I'm going to call it U. Really, I should erase all these Q's and call it something else, but. All right, so that's how you would normalize it. And then let's normalize, might as well normalize everything. So I would go ahead and normalize the second vector, which means I could take any of them and divide by its magnitude, then I'd get the same answer, right? Because They're just scalar multiples of each other. And so the magnitude of this is 6, square root of 6. So I have 2 divided by root 6, negative 1 root 6, positive 1 root 6. And then the last one, U3, is going to be, let's take Q3 prime and let's multiply everything by 6 here. So this is negative 4, negative 4, and I could have just multiplied everything by 3, yeah. Negative 1, negative 1, 1. Maybe you call this Q prime prime. So in any case, this is my vector. This is the nicest vector in that direction. Negative 1, 1. And so just scale that to make it into a unit vector, 1 over root 3. So your third vector would be negative 1 over root 3. Negative 1 over root 3, positive 1 over root 3. Okay? So now we have not just an orthogonal set of bases, but now we have an orthonormal set of bases. So let's see if we can do a little quick summary here. Q1, Q2, Q3 is an orthogonal basis, or orthogonal basis, and then U1, U2, U3 is an orthonormal basis. Right? It's orthogonal and it has unit length.
Oh,
Good? All right. So that really leads us to our last topic, which is the QR decomposition. But are we ready to move on? Are you guys letting this soak in for... it's not going to give you the right answer.
Can we see what the messed up answer is?
There is no messed up answer. All right, so if we want to try to put in the answers, we get 0, 1, 1. The second vector would be 2, minus 1, 1.
nope. You could over there and see
What?
Oh, you tapped over.
You tabbed it and like it screwed you up.
You messed up the previous one.
Oh. And then I don't want to grade it. Well, I can just not assign homework and yeah. Maybe I'll try that. I'll just not assign homework. At the end of the semester, it doesn't matter for you guys.
That's a really bad
Fine,
idea.
because it's supposed to test how well you're, that you were able to discipline yourself to actually do stuff that you're not, forced, so to speak, to do.
All right, that's
Some professors don't advocate for easy points.
so this is what I have, and I don't know how they're. This looks like it's in matrix form, but our solutions are in vector form. So whatever you do in this particular problem in your homework, I'll just go in and manually give you a point for it, and it'll be. Well, it's 1 point.
I was really frustrated.
No. All right, let's get past this.
I'm not going to let him.
Let it go.
Hey, his daughters.
Jeez. Song's in my head now. Okay. So this is our big topic here. If you have an m by n, notice it doesn't have to be a square matrix. If you have any m by n matrix with linearly independent columns, so the column can form a basis for something for your column space, then A can be factored with two matrices, Q and R. So what are Q and R? Q is going to be an m by n matrix with orthonormal columns. And R is going to be an invertible upper triangular matrix. So we need to find R. So here's the process. The process involves the process that we just did, Gramschmidt process, the orthogonalization process. So you go through that process for each of those columns until you have an orthogonal set, and then you make each of those vectors into a unit vector, and then that's your Q. Now, how do you find R? Well, because one of the theorems that we had was that if you have an orthogonal matrix, and I don't know, Hal still doesn't like this name, orthogonal matrix, which is a column of orthonormal vectors. Right? They should have called it orthonormal, but they call it orthogonal. So if you have an orthogonal matrix like we would have gotten in Q, then the inverse is the same as its transpose. So we take the transpose of that, and then we're going to get R by multiplying by the inverse on both sides of this equation. So R is going to be equal to Q transpose times A. So now what's left for us to do is do a matrix multiplication to get R. And hopefully if we do that matrix multiplication, our R would be an upper triangular matrix. Because if it's not, then we might be in trouble. Okay?
And no cake that.
Well, let's do an example of this real quick. And this is done, or half done, so we might as well complete it. In this particular example, we have, I'm just going to copy this real quick. We have this matrix. Let's call this matrix A. And then we have let's see. So we have these results here. So it's a big mess right now, but I'm going to fix it up here. So this is our matrix A, and the U1, U2, U3 provide information about our columns for our Q. So we want to find out what R is equal to, and then we should probably do the multiplication. I do. Because I initially called the non-shrunken, the non-unit vectors Q, where I should have called them something else. And then when I shrunk it down to unit vectors, then I should have called it Q. But so this is your A. And then we found our Q matrix. Yeah, these vectors. I've been not putting the hats on. So our Q matrix is going to be 0, 1 root 2, 1 root 2. I'm reading it down. People usually read matrices across, but 2 root 6, negative 1 root 6, positive 1 root 6, and negative 1 root 3, negative 1 root 3, positive 1 root 3. So that's Q. So now, if we're going to find R, we need to multiply Q transpose times A. So R is going to equal the Q transpose. So let's do the transpose of this. So 1 root 2, 1 root 2, 2 root 6, negative 1 root 6, positive 1 root 6, and where am I? Right here. Negative 1 root 3, negative 1 root 3, positive 1 root 3. And then my A vector is 0, 1, negative 1, 1, 0, negative 1, 1, 1. Oh, sorry, this is a 0. It was a really, really skinny 0. All right, let's do the multiplication. So first row, first column. So that's 0, 1 root 2 plus 1 root 2. So that's 2 root 2. I did do the transpose, yeah. This is the transpose of this. Yeah, the diagonal stays the same.
Oh, it's in the wing.
All right. So the first row and the second column, it's a 0, 0, negative 1 over root 3. And the first row and the third column, 0. Oh.
Yeah, what? It's like 1 over root 2.
1 over root 2. And then the first row and the third column, 0. The last one? All right. Oh, I really, really want to pull out Mathematica right now. Okay. All right. So the second one, there's still a lot. There's a lot of zeros, so it's not too bad. The first one, 0. The second row, second column. So what is it? 3 over root 6. And then.
No, not that. The final one.
What is it?
1 over root 6.
1 over root 6. Okay. So for the first one, you get this and this. So this is 0,
Oh, I see.
negative 1, 6, positive 1, 6. All right, the last one, 0, negative 1 root 3, positive 1 root 3. So this is 0, or negative 1 root 3, 0, positive 1 root 3.
Oh, yeah, because we're trying to remember it's not a-
And then positive, positive, 0. So that's this positive 2 root 3. All right, we found R. R is an upper triangular matrix.
Yay!
The second entry is wrong, but maybe you don't care. But anyway,
This one?
the minus 1 over 2, I think that's supposed to be 1 over 2.
Yeah.
Okay.
Maybe it doesn't matter.
Yeah.
But if you ever do anything with it, it doesn't matter.
Yeah. Well, yeah. If you do something with it, then it wouldn't matter. If I'm just, never mind. Okay, so this is it.
Wait, so we're not going to do anything?
Look,
Well, this is a factorization of a matrix.
this is This is a QR factorization. So we took that matrix A, and now that matrix A is equal to Q times R, where this is Q and this is R.
So that's useful for finding like stuff, right?
Yeah.
For like if you have like the big trust thing that we did for HBA, you can factorize the QR and like makes it easier to find that.
How is it
Sure.
easier to find?
Well, there's just different ways of factorizing the matrix.
Well, if you find this easy to do, then to find the eigenvalues of this would just be the product of the diagonals, and then this is, remember the eigenvalue and eigenvalues for orthogonal matrices are just either 1 or negative 1. So if you don't care about the sign 1 or negative 1, you can just find the eigenvalues by taking the product of this with the diagonals.
So what part of like finding the determinant values is too hard? Like is that just this is just it would be too hard to like big.
Yeah.
Probably, yeah.
Yeah. Right.
Well, we can
No,
try that.
so the question on the exam would probably just doing this process.
And the max size matrix would be 3 by 3.
This is the entire file.
Okay, well, I think we're done with this.
I mean, I think it's 3 by 3. But
Okay, we need to do final review.
All right, your final exam will have 6 questions.
It's so you knew this whole time. Well, now don't us.
No, I was going to tell you. Your final exam will have 6 questions, multiple parts for most of them. The first one would be a system of linear equations, and this will have multiple parts.
So what is that?
Yeah, but what can you tell us what
Like,
a system
because
is?
that's the entire class.
A system of linear equations is a set of 2 equations and 2 unknowns, or 3 equations and 3 unknowns, and you'd have to solve for it.
So is there any special ways of solving this?
There might be a k in there somewhere. Oh, there might also be a finite field in there somewhere.
Thanks. I couldn't say that.
So watch out for k's.
And finite field.
All right,
And P stands for prime number.
p is prime, yeah. All right, problem number 2 would be about just asking questions about rank and null space.
So we should write down
So,
definitions.
given matrices, what can you say about their ranks and null spaces and stuff like that?
So we have to find the ranks in those spaces.
Maybe.
And then what's the etc. part of it?
Stuff.
But we're just
So, etc. would be other things like that.
what's
So
that?
what else is involved? This is starting from 2.4, I think, all the way till most of chapter 2. When they start talking about, is it chapter 2 or chapter 3? Sorry, chapter 3.
Subspaces, bases, dimension, rank.
Subspaces, bases, dimension. That's what etc. is.
Chapter
So starting from 3.5 towards the end of chapter 3 would be information about null space. You know, there's that long list of equivalences,
Yeah.
the fundamental theorem of invertible matrices, that kind of stuff.
Good, I kept mine.
So etc. would include inverses of matrices and fundamental theorem of invertible matrices and stuff like
Will
that.
this be like what we did on the last test, kind of? Some of the stuff? Last test, was it?
It probably will be a little bit different from the last test, because the last test was more finding things. Here, there's a little bit of that, but it's a little bit more theoretical.
Last definition.
All right, the question.
I was just saying, there's no applications, right?
Say it again.
There's no applications, correct?
I'm not seeing applications. No Markov chains.
No closed economic.
And no transformation,
No.
right?
I didn't have room for transformations either, so that got knocked out.
We don't have a take-home, or we do?
All right, the third question would be on determinants.
What's the biggest number of determinant we'll be doing?
I think I have a 7x7 matrix.
What?
Did you guys take your quiz back?
Yes, I did.
No.
7. It's like a
Oh, are you really good at
In the quiz that I had you do, just most of you guys got the idea, but there's some of the quiz. The quiz asks you to find the row echelon form of a matrix, right? And then to find the determinant by doing the row echelon form. Now, what is the big deal about making the matrix into a row echelon form to find the determinant? It's an upper triangular matrix, you just use the diagonal. So some people went and they found the row echelon form, and then they found the determinant by doing that, the first column, and then they take the submatrix, the determinant of the submatrix. So that was extra work that was not needed because it's an upper triangular.
But if you choose the last row,
It's the same thing, but if you use the last row, then you have a submatrix, which is the smaller.
Last row is 0, 0, and then 1. And so then you end up multiplying the diagonal names.
But when you,
Isn't that how you prove it?
So then, so when you're doing row echelon form, you have to keep track of your row swaps.
Yeah, you have to keep track of your row swaps.
That makes it negative and vector.
Right. So that's the whole reason for that row echelon form. But the idea is that it's the diagonal.
Is it just diagonal multiplying?
Yeah.
By the element.
So that's just a little. Never mind. Let's just go number 4.
Are we doing a 7x7 matrix?
I don't know. Number 4 is a diagonalization problem. Do you remember how to diagonalize a matrix?
I think so.
That was one of the quizzes, yeah.
It's like the eigenvalue vector.
If there's a formula for it, then I know how to do it.
Isn't there 2?
So you can diagonalize a matrix. A matrix is diagonalizable if there exists a P and a D matrix so that this is true. Okay, so you need to be able to do that.
And find the key to the eigenvalue?
Yeah, something like that. Number 5 is a question where I give you a matrix and I ask you to find the eigenvalues, the eigenvectors, and then a basis for the eigenspace. Finding the basis for the eigenspace is the same thing as finding the eigenvector, so you just need to put it in those correct terms.
But then we have to describe what it spans, right?
Yeah, that's what eigenspace is. So you can just say the span of whatever vector or vectors are going to be in there.
Oh, you just put span in front of it.
You put span in front of it, that's fine.
Are you going to ask me what
I don't know, maybe.
If you do, I might get it mixed up. I'm like, 3.
So I think there's only one matrix here that you're going to find the eigenvalue, eigenvector for, and then there's one QR factorization.
So for the diagonalization question, are you going to ask if it's what's called a matrix
I think, I don't remember. I don't remember if this has one or two parts. I think it's just one matrix and then you diagonalize it, but you have to find P and D.
Would you say that it could take an entire period to?
Nah, it'll take you about half an hour.
How many K questions would it be? Second.
There's one K question in the systems.
And then we have to like say for what value is K that makes it work.
Something like that. So this is really inconvenient because that's not our usual time that we meet. But yes, the exam starts at 2:10 officially. I will be here before class because I'm giving another test right before this class. So you can come here as early as 1. What's before 2? 1:40 technically is where the other class ends. You can come as early as that. Or hell, you can come earlier. You can come at 11 if you want, and get it done early. Because yeah, they're going to take a test in here.
So it's in a week, right? It's on the 17th.
1 week from today, yes.
In this room.
In this room,
Okay, so
yes.
how many pages?
Well, there's this many questions, so I think each of these will be 1 page.
Oh, no, for notes.
Oh, you guys can get 3 pages of notes.
Because I already have my one. And then are we going to have practice like every other
I was trying to come up with a practice final last night, and my computer ran out of battery, and I got tired. I ran out of battery. So I think by laying all these questions out, you can just go to those particular sections, pull out some examples from the text and from the exercises, problems, and stuff.
Quick clerical question. For the STEM speaking series, how are you going to grade the attendance?
So if you went to 3 of them, then that satisfies your 5% of your grade. And then if you went to more of them, those other STEM speaker series that you attended will go towards your final exam. So if you went to 8 of them, there was 8. If you went to every single one, 3 of them, 3 points counted towards the requirements for the HBA. 5 points would go towards your final exam.
You get 5 points on your
Next question.
Is that your head?
What?
Do you actually have quizzes by chance? Do you post your quizzes? We do quizzes.
Oh, the solutions to the quizzes? You think that'll be helpful?
Yeah.
Okay. Can you send me a quick email, remind me to post quizzes online? So I guess Becca's going to do it. So,
No, like the more people, the more you get.
the more emails I delete. All right. Any other logistics, questions, the time, the place? We're all good? Yeah?
We can still turn in HBAs.
Please.
I already recorded the first 2 HBAs, so you can turn in the, how many did we have? 3? We didn't have 4, we had 4. Okay, you can turn in the last one. Yeah, you can use calculators.
Thank you.
3 pages.
Check everything with my calculator.
Anything else? It's on the paper. Any other questions? Good questions? Yes, calculator. Anytime between 11 and 2 o'clock would be a good starting point. Although the people are going to be here, so if we start running out of rooms, then okay. Yeah.
Well, do you remember I showed you, I raised it.